What's up, YouTube? My name is Haynes, and welcome, my fellow citizens, to the Data Democracy. So today we're going to be talking about something quite a bit different from my other videos and a bit more advanced. I'm going to be talking about overlapping pooled testing for COVID-19 for how we can dramatically increase the amount of the population that we are covering with testing with the same number of underlying tests. So what is the motivation for this problem? And one example is that in the fall, we're going to want to send college students back to campus if at all possible. Other examples are that there'll be airport workers who need to be tested very frequently to protect the population. And outbreaks in both of these settings are basically unavoidable. But also for the population as a whole, currently we're basically testing people who end up in hospitals and then some fraction of people who have symptoms. But many people don't have symptoms or have very mild symptoms and would like to know whether they have COVID-19 or not. Well, you could test every person every day, but likely that's infeasible and it would be very expensive even if it were possible. Recently, several publications and media outlets, including just yesterday, Anthony Fauci, have proposed pooled testing to reach a larger percentage of the population. Now, how this would work is that you pool multiple individuals into the same test, and you do that, across a large population for multiple tests. And if a test comes back positive, then everybody pooled into that test then needs to get an individual test. But can we do better? The inspiration for this pooled design is the probabilistic data structure known as the Bloom filter. So what a Bloom filter is just a fancy implementation that's very compressed of a set of items. And basically what you want from a data structure known as a set is you want to be able to add items into it, and then you want to look at new items and say, is this item already in the set? And it should return true if it is, and it should return false if it isn't. And the probabilistic nature of the Bloom filter is that I have a new item, and I'm going to ask, is that item already in the set? If it answers false, then the item is definitely not in the set. If the answer's true, then it is probabilistically not in the set, but there is some false positive rate where it could say, yes, it's in the set, when really I never added it to the set. And I'll show you how that allows the data structure to be much more compressed than other set implementations, and how we can use that structure to create a pooled testing design that is very efficient. Okay, so how exactly does a Bloom filter work? So the Bloom filter starts with a number of bits with indices, and all of the bits start as 0. And you're going to want to insert elements and then ask whether other elements are in that set or not, because that's the whole point of sets. And so here we're going to insert element A, and the Bloom filter relies on multiple hash functions. Now, what is a hash function? So a hash function maps some arbitrary value into some fixed length value. And in this case, it's going to map some element, in this case element A, onto an index in the Bloom filter. And there are different hash functions, and they can be independent of one another. And so the Bloom filter relies on having multiple hash functions. So in the most basic case, the Bloom filter is going to have 2 hash functions. And so, we're going to insert element A, and the first hash function of element A returns 1, and the second hash function of A returns element 7. And so we're going to set each of those bits to 1, and all of the other bits remain 0. Now we're going to insert another element into this set, and we're going to insert element B, and the first hash function of element B returns 3, and the second hash function returns 7. And you can see that this hash function, this hash2 function, it returns the same value for different input values. And so hash functions can be many to one. They're not necessarily one to one. And the purpose of that is that they can map some arbitrarily large space onto some arbitrarily small finite space. Okay, now that we've talked about hash functions, let's get back to Bloom filters. So we've given the example of how you add elements to a Bloom filter. Now the other aspect of the Bloom filter is that you can ask for a new element whether it's already in the set or whether it's not in the set. And so, okay, let's say that we ask for element C. Now element C, we get the hash function values of element C, and say they come back, they come back 1 and 4. So we look for element 1, and that value is 1. And then we get element 4, and that value is 0. And so if any of the values are 0, then it returns negative. It's true that we did not enter C into the set. And so basically, if it returns false, that the element wasn't in the set, then it really wasn't in the set. But okay, so let's say that we ask if A is in the set. Okay, so A, we already know the hash values of A. It's 1 and 7, and so we look at those values, and they are both value 1, and so it returns true. Yes, A is in the set, and yes, we did enter it into the set. But let's imagine that we ask whether element D is in the set. And let's just say that it just so happens that hash 1 of D is 1 and hash 2 of D is 3. Now, we look at the values of each of those, and it turns out that they're both 1, and so we're going to return true. Yes, D is in the set, but actually we never entered it into the set. And so that's a false positive. And how the Bloom filter works is that it allows some probability of having these false positives while being able to sort of compress the overall data structure to a very small space. And in the same way, we're going to use this structure to compress the number of tests we need for a given population size if we're going to allow a certain percentage of false positives. So how do Bloom filters relate to COVID testing and overlapping mixture testing? So in this case, basically, each bit in the Bloom filter is its own test. Each bit can give you a positive or negative result, and that is a binary outcome, and that is a bit. Now, each sample or patient is assigned to multiple bits according to the hash functions as we previously described. Then any test that has at least one positive patient in it will return positive or give a 1. And so you'll end up with a data structure that looks something like we had before. And then you ask, for all of the patients that you input into that, test design, did all of their hash values, their tests that they were added to, did all of them come back positive? And if all of them came back positive, then you say that yes, that patient is positive, but there is some probability that that patient wasn't positive. But if even one of them comes back negative, then that patient was negative with high certainty. And so in an example like this, you could have 8 tests, and you could have 2 positive tests, the A and B elements, A and B patients in this case, that had positive COVID tests. And then you might have also added maybe 78 other patients who happen to be negative. And so they don't contribute any 1s to this data structure. And in this case, we would have had a 2.5% true positive rate in the population. And then we would have also called, on average, 11 false positives in addition to those 2 true positives. And as these setups grow, this is a sort of simple setup. As these setups grow, then they can get a bit better. And in many reasonable scenarios, such as dorms or airport security, you might have maybe up to 4% true positive infection rate and you can use 10 times fewer tests and have a maximum of a 1% false positive rate from the test design. So it turns out these ideas are related to a subfield of statistics known as group testing, very surprisingly, which I was unaware of previously, and there is already a preprint publication out on a setup that is very similar to this, but not quite the same, and I'll cite it right here and you can go and read further. You know, if nothing else, it's an example of how math can solve real-world problems in interesting ways, and if you liked it, please like and subscribe, and I'll see you in the next one.